Welcome back everybody to another video lecture from Ms. Semino. This afternoon we're going to go ahead and discuss changes in enthalpy, remember that was our delta H, in different phase changes. So as I mentioned, today we want to be classifying the enthalpy change that occurs when a substance melts, freezes, boils, condenses, or dissolves. This is not really a phase change, but there is an enthalpy change that's associated with dissolving solutions, so we need to learn about that. And then remember, I did say that there was a little bit of math for this chapter, so we are going to be doing some calculations. So it says solve here, so there's some calculations that go along with these, but they're not really that bad. You're going to be fine on this lecture as long as you're just looking at the delta H. You know that that's enthalpy, and then you look at the subscript that's written next to it, and as long as you understand what that definition is, you should be able to calculate these just fine. So talking about the heat and changes of state, so the first one we're going to look at is delta 8 FUS, and so that's standing for fusion. Remember that fusion was another term for melting, we saw that earlier. So when we see this, this is technically standing for the molar heat of fusion. And so the formal definition is the heat absorbed by 1 mole of a substance in melting from a solid to a liquid. So when you see the molar heat here, it's telling you that it's 1 mole. Fusion, we're going from the solid to that liquid phase. And so then if you look at the equation that we're going to need here, here's our heat, okay, times your number of, equals your number of moles times your change in enthalpy. And so these are actually just values that are given in your textbook. Our textbook for honors is not the same page, but we do have a table, and on your worksheets you'll be given those delta H values as well. The next one that we need to look at is the delta H of solid. So this is really the molar heat of solidification. And so this is equal to our heat is equal to the moles times the delta H solid. Again, this is going to be a value that's given from your textbook. So this is the heat that is lost when 1 mole of liquid solidifies or freezes to a solid. So here is just a quick little note. We have been seeing our delta H's in values of kilojoules per mole. Okay, so our enthalpy change is usually given to us like this. Sometimes in different textbooks and worksheets, you might see it in kilojoules per gram. So on the previous slide, we were saying that this was Q equals moles times delta H. Okay, and that's because that would go with this one down here. But if they end up giving you the grams, you can also use this equation. So a fundamental key point to keep in mind is that the heat absorbed by melting a solid is equal to the heat lost when the liquid solidifies or becomes a solid. So your delta H of fusion is going to be equal to the negative delta H of the solid. So kind of think of this in the molecular level, because that's how I always want you guys to do this. So if we are going in this direction, if we're going from a solid to a liquid, remember that we're from a solid to a liquid, we're going to be breaking those particles. So we're going to need to be adding energy to that system, and so we're going to have a positive delta H value. On the other hand, if we're going from a liquid to a solid, we're wanting to release some energy. And remember, this negative means that it's an exothermic reaction and that heat is being released because those particles are getting close together. So the particles themselves are losing energy, so that energy has to go somewhere, so it normally exits the system. Remember, we talked about the system and the surroundings. So the heat exits the system going into the surroundings, which is why we have heat that is leaving the system. So here on this slide, here's a little problem. It says how many grams of ice will melt if 2.25 kilojoules of heat's added. So an important concept to remember is that your temperature of your liquid's not going to change unless like the last small piece of ice is melted. So your temperature is going to remain constant at 0 here. So when we look at our knowns and our unknowns, our initial and final temperatures are going to be 0, like I said, because that liquid is going to still be at that 0 degrees until every last piece of ice is melted. We can get from our textbook or from our thermochemical equation down here that your heat of fusion is 6.01 kilojoules per mole. They're telling us that we added this much energy and we're looking for this mass. So if you remember the equation that we just used on the last slide, it was Q equals moles times delta H. And we want to use moles here in this case because we're using moles here. But since we are looking for grams, we are going to need to use the molar mass of ice, or I guess I wish they would have said water there, because we know that water has a molar mass of 18.0 grams. So if we look at the calculation that they did here at the bottom, we're taking our mass. Here is the amount of heat that is added. Okay, then we are going to take the amount of the heat of fusion, 1 mole, kilojoules. And remember, I want to draw this, hang on a sec. Remember, we can flip these factors, like this delta H here is being flipped. The moles are being put on the top and the 6.0 is being put on the bottom, so we can cancel out their units. And then here is the molar mass of our water, and that's going to give us 6.74 grams of ice that was melted when we added our 2.25 kilojoules of heat. So heats of vaporization and condensation. So when liquids absorb heat at their boiling points, they become vapors. So we've talked a lot about that. A vapor is just another word for gas. So you'll be shocked to learn so far that there's a delta H for vaporization. So the molar heat of vaporization is equal to the amount of heat necessary to vaporize 1 mole of a given liquid. So then here is that same equation that we're looking at. Notice we just changed our subscript here. And again, there's specific values for these that you can look up in your textbook. Not this page in our textbook, but you do have a reference in your book. So remember that condensation is the opposite of vaporization. So if you're condensing, your particles are coming together. If you're vaporizing something, your particles are getting farther apart, turning into that gas. So here's the definition of the, sorry about that. So here's our definition of the molar heat of condensation. Here you guys can see that subscript is for condensation. So this is the amount of heat released when 1 mole of vapor condenses to a liquid. And then here's that equation for that. So if you notice here, just like when we were going from a solid to a liquid, we were saying that they were opposites of each other. Here we can see that when we're going from a gas to a liquid, it's also going to be opposite. So the same thing applies. If we're going in this direction, we are having the particles go further apart, so we're going to need to be breaking bonds, and so we're going to need to be adding heat or energy. If we're going in this direction, the particles are condensing or they're getting closer to each other, so we're actually going to have to be releasing energy because the particles are slowing down, and you have to put that energy someplace else, not in the particles, so that's why it's being released. So I think that this slide is pretty interesting because it puts these values for delta H vapor and condensation into some perspective. So here it says that the large values for water, their delta H for vaporization and their delta H for condensation, is the reason that hot vapors such as steam are very dangerous. So you can receive a scalding burn from steam when the heat of condensation is released. So when you go from a gas to a liquid, remember that we're releasing lots of energy here, so that's a pretty sizable amount. So that's why I did this once. My husband still laughs at me to this day. I was making a baked potato in a Ziploc bag in the freezer, and I pulled it out, and it was really hot, but when the steam escaped, and it condenses, I really got a bad burn on my hand, and that's because it has such a high energy content associated with it. So the last delta H that we need to talk about is the heat of solution. So heat changes can also occur when a solute dissolves in a solvent. Sorry, I hope you guys can hear me over that bell. So the molar heat of solution, delta H solution again, is equal to the change caused by the dissolution, I like to just dissolves of 1 mole of the substance. Oh, look, it's the same equation again, just with a different subscript. So there's a good example on the next slide. Sodium hydroxide provides a good example of exothermic molar heat of a solution. On this slide, we're going to talk about that heat of solution that we were mentioning previously. So if we were to take our sodium hydroxide, add it to water, our ions are going to separate into sodium and our hydroxide ion. We actually see that 445.1 kilojoules per mole of energy is being released. And it's being released as the ions separate, so by dissolving and interact with the water. And then it becomes so hot that the reaction steams. So let's look at a picture of this on the next slide. So when you make this mixture, it's kind of interesting. If you look down here, you have your beaker and you're adding your sodium hydroxide here. But notice that they're having a larger beaker down here with ice in it. It helps control that temperature to make sure that nothing breaks. I hope this video was helpful. Please remember that there's a lot of delta H's, but if you just look at the subscripts and remember what the vocabulary term is for that, you'll do just fine. Good night.